Welcome, everybody. Hopefully you can hear me. Before I introduce Eric for this colloquium, I just wanted to say a couple words about the PCC. So I'm Kyle Armour. I'm the interim director of the program on climate change at UW. So what we're doing today is some kind of blend of the ESS colloquium and also a program on climate change colloquium series. And the whole idea behind this PCC colloquium series is to kind of have talks that rotate around campus and kind of introduce people to different audiences. So hopefully some of you are here today because you heard about this through the PCC listserv and you wanted to come see Eric talk in his own colloquium series, but you wouldn't have been here otherwise. So welcome to those folks. Just a few words about the PCC. So the program on climate change has been around for 25 years or so. The whole idea is basically to, we're on a campus that does so much climate research across so many different units, so many different departments, different colleges. So we are your home if you are doing climate science research or just climate curious, as I am, and you want to connect with other people doing climate science research, do interdisciplinary collaborations. We have a lot of educational programs. We have classes for graduate students and undergrads. We have a climate minor. We also have a graduate certificate for graduate students. We also fund a lot of research through grants to faculty members, also grants to graduate students. So come talk to me if you're interested in hearing more about those things. So anyway, I just want to introduce Eric and say thank you very much for giving one of these joint colloquia between ESS and the PCC. So Eric got his PhD sometime in the late 20th century, I believe, at this institution. After doing a short postdoc at CU Boulder, I think he went to Pennsylvania to do a faculty position briefly before coming back as a faculty member to UW in 2001. His work is well recognized by the community. He's an AGU fellow. He's done a lot of really exciting work. When I think of Eric, I think of someone who has deep expertise in glaciology, isotope geochemistry, but also he's a climate dynamicist. So he's somebody who can really go across campus. He is. He's shaking his head, but I think he is. He knows about the ocean. He knows about the atmosphere. He can really speak across all those communities. So he's really a perfect representation of what the PCC is all about in terms of the interdisciplinary strengths and also disciplinary depth to really understand the climate system. So thank you again, Eric, for giving this colloquium, and I'll let you take it away.
Thank you.
Oh, also, welcome, Eric.
I think this is that thing working now? Yeah. Thanks, Kyle. I feel like we should stop there. It doesn't get any better. Everyone can leave. No. So, of course, this isn't working now. Well, there it is. Okay. Sorry. Okay. A bunch of you have seen different components of what I'm going to talk about. Hopefully there will be enough new that it'll feel like it was worth your while. When I thought about what I wanted to talk about, I just had a paper provisionally accepted with my former student, Brad Markle, and I love this paper, and I'm going to talk about it a little bit towards the end. But I really just had this overwhelming feeling, man, ice cores are really magical. And the main thing I want you to get out of this talk is some excitement about that. This is a photo, of course, of an ice core. This actually happens to be one from British Columbia in Canada, which I'm not going to talk about. I want to acknowledge a few folks. Well, I already mentioned Brad Markle. A couple of other former students, Jem O'Connor, who I think is here, who's now a postdoc in oceanography, Dave Schneider, who was my first graduate student at the University of Pennsylvania before I moved, and he followed me to UW. Of course, lots of other collaborators, many faculty here at ESS and atmospheric sciences and oceanography. I work a lot with folks in the British Antarctic Survey as well, but I just wanted to highlight those three folks in particular because they've taught me a lot over the years, and I'm plagiarizing their work here. Funding from various sources. And that's just a nice photo from Antarctica by Brad. So the ice core record begins in the 1960s with the drilling of the Camp Century core. And we have a film out about this, and we're going to do a screening in the spring. I'll let you know. But one of the really key results in the development of ice core science in particular and climate science in general is the records from the Vostok ice core in Antarctica. So this is the location of Vostok. The first paper came out, I think, in 85. But this is 87, and this was a big deal. So I want to talk you through it a little bit if you're not familiar with it. So, well, it says 160,000 year record of atmospheric CO2. This is the key plot, age going back 160,000 years on the x-axis. The deuterium isotope ratio of heavy hydrogen to light hydrogen. Equivalently, you can use the ratio of heavy oxygen 18 to oxygen 16, and you can see there's a temperature scale here. So this record is based on the relationship between temperature and the isotopic composition of water recorded in ice cores. And it shows you quantitatively, but also qualitatively. One could argue about the scaling a little bit. This is the warm present. This is the last glacial maximum, fluctuations through time, the last interglacial period when sea level was probably certainly 2, possibly 6 or even 9 meters higher than it is now, the previous glacial period, and the CO2 record. This was an important paper because it was the first paper to really demonstrate the correspondence between those two things, which is now people take for granted. The value of CO2 at about 190 parts per million during the last glacial period was predicted pretty well by Svante Arrhenius in 1896. So this was a validation of a 100-year-old theory. And even though I think it is easy to forget, this stuff is fundamental to our confidence about our understanding of the climate system in general. In fact, very recent papers, including one that Kyle is part of, use essentially this record as part of the constraint on climate sensitivity. On the upper right is another really famous, important plot showing temperature at various locations in Greenland and Antarctica, and the concentration of hydrogen, the delta deuterium value, the ratio of heavy to light hydrogen, and heavy to light oxygen on the y-axis. There, it's essentially the same thing. They're just scaled by about a factor of 8. So there's an empirical relationship between temperature and isotope values, and you can use that to get a proxy to determine temperature in the past from ice core records. Now, I started grad school in 1989, a couple of years after this was published, and I approached Minza Stiver, my wonderful, fantastic, brilliant advisor, who was the most highly cited geoscientist on Earth for almost 20 years, more than 20 years, I guess I wrote there, I think it must be. This is what he said to me. He's like, I'm happy to have you as a student, you can work on the Greenland ice cores, but this is not important work anymore, that's important. I'm sure you all know a lot has happened since, and I'm actually not even going to talk about the Greenland ice cores, because all the important work in Greenland's been done. The purpose of this talk, this is just a nice photo from the South Pole of a backlit snow pit to illustrate the stratigraphy that we're dealing with. Here's the purpose of the talk. Ice core science has advanced a lot since those early days, and those were already the late days in some ways. One of the oldest measurements developed in the 50s, the oxygen and hydrogen isotopes of water that I just talked about, remains one of the most useful. And I'm going to give you 3 examples of how we're using ice core isotope records to learn cool things about climate and ice. And this, again, is kind of the motivation for my title, Ice Cores Are Magical, because I'm constantly amazed that we're continuing with this old measurement to learn new things. So just very briefly, for those not familiar with this, the water isotope paleothermometer, that correlation between temperature and O18 or deuterium, can be essentially explained by the evaporation of water from the ocean, which preferentially the lighter isotopes get into the vapor phase, and then preferentially the heavier isotopes fall out, and the net result of that is that lighter isotopes dominate over the ice sheet, and because evaporation and condensation are temperature dependent, this is a temperature dependent thing. It's intimately tied to the physics of the water cycle, and the water cycle is intimately tied to the physics of the entire climate system. So this is a proxy for local temperature, but it's really a proxy for large-scale climate processes, just as other variables in the climate system, like pressure and temperature, are fundamental. This is pretty fundamental. We can and we do use more advanced modeling tools than this simple Rayleigh fractionation scheme. A couple of examples here on the simple end, although a pretty complex model, which Brad Markle called the simple water isotope model because it means swim. That's sort of one end member. Another is, high-resolution simulations with GCMs, in this case done with the weather research and forecasting model with code developed by Peter Blossy in atmospheric sciences. I'm not going to talk about that in detail. I'm just saying, yes, I know it's not as simple as Rayleigh fractionation. So example number one. One of the important questions glaciologists have been claiming is important for my entire career is the question of whether the Western Arctic ice sheet collapsed during the last interglacial period. We have lots of circumstantial evidence that it did, like sea level was higher. And there are a number of modeling studies which suggest, here's the ice sheet today, here's a model simulation of what the ice sheet might have looked like 125,000 years ago. And one of the things I did about 10 years ago with a bunch of colleagues in atmospheric sciences, including Kat Hybers, who I think was the second author on this, we showed that if you run an atmospheric general circulation model over an ice sheet topography like this and compare it with an ice sheet topography like that, you get a change in the circulation. So this is the surface wind field. And in colors is the potential temperature. And what it's showing is that when you lower the topography here, you create a cyclonic anomaly, which brings more moisture in this direction, and there's more flow off the continent in that direction, and that has implications for what the surface climate is like. And the basic proposal is if we go and drill in the right place, such as here at Hercules Dome, we can perhaps see whether there's evidence of this happening in the past. So a few years later, many years later, we advanced that work. This was led by a postdoc of mine, Marina Deutsch, who's now at the University of Vienna. And we did the same kinds of simulations that I just showed you, but in this case, we were nesting a high-resolution weather forecast model within a global GCM. And these aren't so important for my purposes now, but this is the wind, essentially. This is the stream function, precipitation, 2-meter temperature, and water isotope values, O18 in this case. And this is the blow-up of that section. And even though the focus of my work had been demonstrating that we should go drill an ice core at Hercules Dome, which I wanted to do for about 20 years, and we haven't yet done, that's located here. One of the findings was that in the event of a waste collapse, a lowering of the Western Arctic ice sheet, that cyclonic anomaly will bring a lot of warm, moist, high O18 water to this particular region, which is called Skytrain ice rise. And colleagues in the UK drilled a core there. They're faster than us. And this is what they found. This is the Holocene. This is the last interglacial. And this is the anomaly relative to the sort of Holocene baseline. So there's higher values in the last interglacial, as was predicted, and by about the right magnitude, a couple of per mil in O18 compared with the Holocene. So the climate's similar, last interglacial, current interglacial. These simulations say if the ice sheet were lower, those values should be higher. You, of course, want to compare this to some control, and the control is other ice cores far away from the Western Arctic ice sheet where we don't think there was a change in elevation, and that's shown here. So here's a couple of ice core sites, Holocene, last interglacial. Values are higher, the scale's the same, but they're not as much higher. So I was very excited by this. We made a prediction. We got the answer that we predicted. There's all sorts of details which maybe make this wrong. I don't know. There's more work to be done, but I was very satisfied that to first order, I like to think science works this way. You make a prediction and you get an answer that is consistent with it. So that's example one. Example two, which I'll talk about in a little bit more detail, that was about changes to the Western Arctic ice sheet in the more distant past. Not geologically distant, but atmospheric scientists might think it's distant. The Western Arctic ice sheet may be collapsing now. Ice melt in Antarctica today is not driven by warmer air temperatures like it is on alpine glaciers or in Greenland, most of Greenland. It's driven by the access of warm water to the underside of the floating ice shelves that come off the Antarctic continent. And the region where this is happening the most is the Amundsen Sea region over here. The red here shows the thinning rate of the floating ice shelves. And the glaciers, which aren't shown because there's no data shown there, are also accelerating as a result of that. So that's contributing to sea level rise. The colors around the continent here show the temperature of the warmest water at whatever depth it is. And in this part of Antarctica, that's circumpolar deep water, which is a couple of degrees above the in situ melting point of ice. Evidently, changes have occurred somehow in the climate system such that you're getting more of that circumpolar deep water melting the ice. And the reason we know that must be true is that if you look at the current rates of retreat, if that had been going on for 100 years, they would be gone, or at least much further back, not gone. Now, if you stick with modeling world and you don't use data, you can tell stories about why this is happening, which go something like this. Well, we know that the reason circumpolar deep water is present and is upwelling around Antarctica is because there's a mean westerly flow in the atmosphere. This is the surface stress, but essentially the same thing. The wind is doing this, it's pushing on the ocean. The Coriolis effect means the surface water goes to the left in the southern hemisphere, so something upwells, and this is the mean temperature profile. So even though it's blue, this is still relatively warm water. It's upwelling along the coastline, contours of the density. And we know for sure that the westerlies have increased in the last several decades. And we're very, very confident that that's actually a forced response. The climate system is responding to energy changes from depletion in the stratospheric ozone and greenhouse gases. So there's a strong link between that circulation pattern and increasing westerlies around Antarctica. So you might think we're done. I'm just going to show you a couple slides, which I'll talk more about later. But the region that we're talking about here, right here, when you zoom in on the bathymetry, it looks like this. So here are the glaciers that are changing the most. Pine Island and its Thwaites are the most famous ones. They're flowing off the ice sheet into the sea. And this is the continental shelf here with depths around 500 meters. And then there's the deep ocean there. And more or less the same map. This shows the presence of circumpolar deep water in the deep ocean and a particular data set observations / contours showing the flow of the circumpolar deep water along old glacial troughs in the continental shelf and up towards the ice. So that's sort of the picture that we're trying to understand. Like how do changes in the delivery of water, apparently that's increased. Why is that? What has happened in the climate system? So my contribution to this began decades ago because I was involved in this project to drill ice cores all over West Antarctica, and there are many more that have been drilled over East Antarctica. The reason this project was important is that there was then and is still only one permanent weather station in this huge area that's about a third of the size of the United States. It's a bird station, and it only goes back to 1957, which is starting to sound like a long time ago, but really isn't from a climate perspective. So amazingly, we have far more weather data, climate data from ice cores than we do from direct observations in Antarctica. This plot shows the average oxygen 18 variability. So I've subtracted the mean from all the records, placed them on top of each other. The black line shows the average O18 variations for 200 years. The gray background is the decadal mean to give you a sense of the differences among the cores. And for context, it also compares the weather station record, temperature record at bird station in West Antarctica, and kind of roughly the time period of modern climate reanalyses, which are only valid back to about 1979 in this region, in the high latitudes of the southern hemisphere, and modern observations of what's happening to the ice. This is a huge increase in context, right? If all you knew is this, you would say, it's warming up, the circumpolar winds are increasing, we're done, we understand everything. And as soon as you look at this, you realize there's a huge amount of variability. And it's not at all clear that there's actually a change in the sense of a long-term change. Maybe what we're seeing in Antarctica is just part of the natural variations of climate. I don't believe that, but I don't think we've proven otherwise yet. And to be good scientists, we need to know before we can make such claims. This is really one of my goals in the next 5 years, is to be able to make that claim or to prove that it's wrong. Okay, so we have an ice core record, a bunch of high-quality data, which we know is correlated with temperature. You can see a similar warming pattern here, increase there. But the circumpolar deep water is not being affected directly by the temperature up on where it's snowing. It's affected by circulation, winds, sea ice, snowfall, precipitation over the Southern Ocean, temperature, et cetera, et cetera. We can use some statistical methods to take the ice core records and ask, how do you create an ice core record like that? What's happening in the climate system to wind up with high O18 values in this part of Antarctica and lower values in that part of Antarctica? And the method that we're using essentially relies on the fact that things are correlated in the climate system. So this is the covariance of the Amundsen sea level pressure, the green box here. What is the pressure in this stormy part of Antarctica near the coastline of Antarctica? What is this covariance with temperature everywhere else? And unsurprisingly, the temperature in Antarctica is more connected to the sea level pressure near Antarctica than it is to other places. Although there's some neat other correlations, like the tropics, that's the ENSO region, and it affects climate down in Antarctica. This is just a blow-up of that same thing for Antarctica. And all the dots here are ice core records and various other proxy records, trees, corals, etc. Because ice core O18 records are correlated with temperature, we can use these relationships to estimate sea level pressure and other aspects of the climate system in the past using these covariance relationships. And the way that we did this, and this is work led by Gemma O'Connor and her PhD, is a sort of new method called paleoclimate data assimilation, which here at UW was developed by Greg Hagum with a bunch of other people involved, going on 15 plus years, I think, really. It takes advantage, as I said, of the covariance between proxy data, ice cores, et cetera, surface temperature, and other climate variables. It's a formal method adapted from weather forecasting. See Greg's paper. We'll go talk to him if you want to know more. Gemma's PhD work took the ice core records and other proxy data from around the globe, used climate models, and said, let's figure out what really happened. Not what the climate model said, but what the climate model said could have happened that's consistent with the data, and use that to estimate things we think might be important for the ocean and therefore the ice sheet. And to take a lot of work and compress it into essentially one slide, what she found is that it's true that over the last century, the large-scale circumpolar westerlies have been increasing. We knew that. It's nice to see that it's found in these records. And I should just describe quickly what I'm showing here. The black line is observations from satellites, weather stations, et cetera, going back into the 60s. And the various other lines are various iterations she made using different climate models, different assumptions, et cetera. But the basic result is, no matter how she looked at it, there's an increased westerly wind happening, but there is also a decrease in this thing called the Amundsen Sea Low Index. This is a strengthening in this direction of the Amundsen Sea Low. What's the Amundsen Sea Low? There's the Aleutian Low that we're all familiar with that brings weather to the northwest in Alaska. Here's the Amundsen Sea Low on the other end of the spectrum. It's the same kind of phenomena. It's the sort of average position of storms in that region of Antarctica that bring moisture, heat, et cetera, up onto the western Arctic ice sheet and affect the sea ice and the oceanography. Associated with a strengthening of the Amundsen Sea Low happens to be stronger northerly winds in this region of Antarctica that we're interested in. So what's shown here is the sea level pressure change, the trend per century in hectopascals, the surface winds, and then the coast of Antarctica. And this is just a blow up of that region. So again, this is similar to what I just showed, but now she's actually plotting the meridional wind anomaly. So by convention, when the meridional wind increases, that means it's going northward. So this is a decrease in the northward winds, it's an increase in the southward winds, so flow towards the continent. I showed you before ocean temperature in the Amundsen Sea. So how might those winds affect the flow of water onto the continental shelf? Well, Gemma's answer in a really beautiful study, I mean, I'm a co-author, so of course I'm going to say that, but I think I would think that if there weren't, I'm sure I would. The reviewers liked it. Just published, I think in October, September. Gemma did a bunch of really well-crafted, idealized ocean model simulations using a high-resolution ocean model and asking, what does the ocean do in this region when we change the winds in a variety of ways? And this was not the result we expected or were looking for or anything, but what we found is that the northerly winds in this ocean model drive more circumpolar deep water onto the continental shelf. Now, I should be careful and use that word drive advisingly. You don't expect, because of the Coriolis effect, winds blowing in that direction to blow ocean water in that direction, right? It goes to the right or the left, depending which hemisphere you're in. So what's actually going on here is a detailed and complex interplay between the winds and the sea ice and the heat fluxes and the salinity fluxes and the ocean circulation itself that I'm not going to go into, but you can read her paper, which is fantastic. Gemma also looked at a bunch of previously published simulations and found that even though those publications hadn't recognized this, other simulations with a very similar model, I should add, show the same thing. So the upshot is, this might not be the full answer. There's more to it, but this work ultimately comes back to those ice core records, those isotope records that we obtained going on 20 years ago. And they're still useful, and we're learning things from them that we didn't plan on at all, except in the most vague way, like I want to understand climate variability. Last point on this, I think, which is that this is a work in progress, but there is some evidence to suggest that this pattern of increasing Amundsen Sea, a stronger Amundsen Sea low and increased flow in this direction towards this critical part of Antarctica is actually a response to large-scale climate forcing. So in some models that have been published, you see when you increase CO2, you see the well-known increase in the circumpolar westerlies, which is represented here. This is you can think of this as the pressure. It's the height of the 500 millibar pressure surface. The surface pressure will look similar. So this is increased westerlies, and here's the Amundsen Sea low right here. Okay, so that was example 2. Example 3. This is the paper that caused me to go, oh, this is so it's magical. We now have 10 records from the Antarctic ice sheet of water isotopes that go back between 55 at South Pole there and 160, and actually in some cases 800,000 years. This shows the surface temperature for all of these sites derived from the water isotope records. One of the things that I just think is so beautiful about this is that in the model that Brad Markle developed for his PhD, you can give it the water isotope values, the deuterium and the oxygen, run it through the model, and you will get not just a reasonable looking thing, you'll actually get the correct mean annual temperature today, plus or minus a couple of degrees. This was not tuned to do this. This is what the physics dictates. I'm kind of like, really? I need to reread this, but anyway. So this is Brad's reconstructions of temperature for all these different ice core sites going back 160,000 years. And we have uncertainties, et cetera, on them, but we're very confident that this is the right picture. And I should add, actually, that for one of these sites, Waste Divide, located right here, that one, we have independent constraints on the glacial to interglacial change from borehole thermometry done by Kurt Cuffey, who many years ago was a student here. We actually get the same number, plus or minus 0.1 degrees. It's 11.2 degrees, and we got 11.3, or vice versa. So we're lucky, or we're doing something right. There's Brad. This is the title of the paper that's hopefully coming out soon. Temperature-dependent feedbacks drive the pattern of Antarctic temperature change. And I want to just run through this because, as I keep saying, I think it's beautiful and kind of magical, and I think we've learned some neat things from it. I'm plotting here the surface temperature for each of these different sites where we have ice core records that are well dated and well constructed, and we have high resolution. And this is the magnitude of the glacial interglacial temperature change from the graph that I just showed you. And there's error bars on here. And this is not a best fit line. This is a theoretical prediction from the nonlinearity of the water vapor feedback. And I'll talk you through this in a bit. You'll note there's one kind of outlier here, which is that one, and I'll come back to that. So what is the nonlinearity of the water vapor feedback? This plot shows the surface temperature and the upward energy flux for two different things. This is the theoretical curve for essentially black body radiation, except nothing is a perfect black body, so it has some emissivity, which in the case of snow is actually very close to 1. It's about 0.98 to 99. So it follows this classic sigma t to the fourth curve. And this is data measured from satellites, and in one case it's just the raw data, in another it is reanalysis data from climate forecast reanalysis work. They agree with each other very well. So this is the energy leaving the surface. This is the energy leaving the top of the atmosphere. The difference between those two things is the greenhouse effect. And it looks like this. And it's mostly from water vapor, right? The really interesting part is that there's curvature at temperatures below about minus 20 degrees Celsius. And another sort of interesting thing is that if you actually look down here, these lines cross each other. That's a negative greenhouse effect. I don't really understand it. It's been published about. The math makes sense, but I can't get my head around it. So the presence of CO2 cools the surface in that case because those lines are crossing. In a typical sort of textbook, simple climate model kind of simulation or exercise, the relationship between the magnitude of the greenhouse effect and temperature is treated as a straight line. In other words, their derivative is a constant. But as you go towards low temperatures, it's not constant, it's nonlinear. As I said, note the curvature. So the greenhouse effect, mostly because of the temperature dependence of water vapor in the atmosphere, Clausius-Clapeyron, you can think of this as a feedback, right? Like, in fact, it is called a feedback. You do something to warm the planet. Black body radiation, the Planck effect, says, I have too much incoming energy, it's warming me up, I'm going to have to warm up and radiate more. But the greenhouse effect then suppresses that radiation. And if the temperature is increasing the greenhouse effect because it's increasing the water vapor, that's the water vapor feedback. It's well known, it doubles the climate sensitivity versus a planet that has no atmosphere. This is what a plot would look like of the change in temperature as a function of the surface temperature, the initial surface temperature, for a range of energetic forcings, whether radiative forcings or just like there's some heat source, there's warm air coming in, warming the surface. How is it going to respond? This is how it should respond. That's the Planck response, essentially the black body response, except for this emissivity value. So you would predict, if there were no atmosphere in Antarctica, that places that are cold will warm and cool more than places that are warm for some given increase or decrease in forcing. When you add the greenhouse effect and you treat it as the feedback, the derivative of the greenhouse effect versus temperature winds up in the denominator here, and you predict for a given forcing this pattern of surface temperatures, which says that warmer locations will change temperature more than cold locations for a given forcing. So here's all the temperature records put on top of one another with the mean removed. And you can see that, they agree with each other really well, but there are some differences. And you can kind of get the impression that the warmer sites in yellow have larger amplitude than the colder sites, which is consistent qualitatively with that prediction. If you get rid of the noise by taking the first principal component, so this is a simple statistical method for asking what's the sort of common pattern here, get rid of the noise. And then you ask for each ice core, how important is that first principal component? What is the relative weighting, which is what's plotted here. So the weightings times that time series. It really makes it clear that the warmer sites have higher amplitude than the colder sites. And it turns out this is true at all timescales that we can discern, like century and longer, that's the pattern. And it always follows along that line. And you can show this by just plotting the mean temperature versus the change in temperature for a given part of the time series versus the mean temperature for all the different ice cores. That's PC1. So this is the first principal component relationship. How much does the temperature change versus the mean of all of the sites as a function of the mean temperature? This is the gain. If the average temperature change is 20 degrees, warmer sites will be, say, 20% greater than that, so 24 degrees, and other sites will be 0.8. And the prediction from the greenhouse effect feedback equation that I just showed you is in black. It's essentially a perfect relationship. Incidentally, this is something that I'm trying to figure out now. GCMs don't really show this. In fact, Brad did some of this work during his PhD, and we struggled for a very long time and kind of set it aside because you run GCMs and you don't see this temperature pattern. Turns out, more recent GCMs see it, but also simulations done at high resolution with more layers in the atmosphere. It's quite clear. I think what is going on is that the amount in the vertical structure of water vapor in lower resolution GCMs is just wrong. We know that water vapor over Antarctica is a problem. I don't know if that's the right answer, but in any case, that simulation does a really good job of capturing what we see. So if we add the noisy data back in, again, this is really across all timescales, but I'm just putting the last glacial maximum to Holocene, the data that I showed you before, on top to show you that relationship. And to then highlight the West Antarctic ice sheet divide site here, which is deviating more from that line than the other sites. We think this is elevation change, and we can use this, again, to go back to my first love, which is the ice sheets. If we take the West Antarctic ice sheet divide isotope record converted to temperature and subtract it from the first principal component of all of the ice cores, or just equivalently, take the average of all the ice cores and subtract waste divide from that. The residual is some curvy thing that looks like this. In temperature, you can then convert that to an elevation by dividing by the dry adiabatic lapse rate. So the simple fact that it's colder when you go higher up. There's uncertainties to what this value should be, but it's not going to change the basic picture, which is that this is an estimate based on the comparison of ice core records and how they deviate from that theoretical line of the height of the top of the West Antarctic ice sheet over the last 30,000 years. And this is important for a number of reasons that I won't go into, other than to say this, I think, is a strong constraint on ice sheet models. One of the most uncertain parameters in ice sheet models is the stickiness of the bed, how easy it is for the ice to flow. And in fact, it varies by, I said I wouldn't go into this, but it varies by orders of magnitude in parameterizations that people use. So it's a really uncertain parameter. I'm showing two examples of ice sheet model output where we looked at a bunch of simulations and found ones that match. But it turns out that it matters, of course, not just what the slipperiness of the bed is, but also what accumulation time series you use. So you're simulating the ice sheet with variations in temperature and snowfall. And shockingly, a really common thing to do in ice sheet modeling is to use the average from the Dome C ice core because it's the longest record. It's really far away. It does not have the same accumulation history as Waste Divide. And I actually had to beg a colleague, Torsten Albrecht, to do this. Like I said, try it. Put in the observed West Antarctic ice sheet precipitation and show me the results. And it actually doesn't matter that much what slipperiness parameter he gets. He always gets something that's similar to this. And the reason is simple. It's cold back here in the glacial. It starts snowing. The ice sheet builds up. And then this is where the slipperiness comes in. It's building up and building up. It's starting to flow faster. How long does it take to flow affects how quickly it drops again. So again, this is preliminary, but it just shows you that the importance of the ice core records to figure out, first of all, why do they look like that? That was the initial idea. But then that changes how we think about what they mean relative to one another. Because in our calculation, we're making calculations relative to a line that looks like this, colder sites, warmer sites, rather than a line that, say, that looks like that or that. All of that would change its results. And we didn't tune this to make it look like this. It's a very satisfying result. Okay, summary of key results. Antarctic ice cores show West Antarctic ice sheet probably collapsed during the last interglacial period. There should be a D there. Winds in the Amundsen Sea region have changed in the last century, consistent with ocean forcing glacier melt. The water vapor feedback explains the pattern of Antarctic temperature change, with implications for ice sheet elevation and possibly pointing to issues with GCMs that run at low resolution at least. And I just want to end by saying again, what I hope you have learned from this is ice cores are pretty cool, and isotope records remain an incredibly powerful constraint in the climate system. And it's exciting to see there's more and more development of water isotopes in models, for example. NCAR has just launched a new initiative to include this in the next generation. And I think it's really going to be useful. And many of us have been begging for this to happen for decades. And it's really great that more progress is being made. They help answer critical questions about the planet and cryosphere. And they really do provide quantitative, not only qualitative constraints. And we should use them more. And it will stop there. Yeah, thanks. That's a great question. So, of course, one can take all of the cores and look at all of their deviations from theory and come up with a bunch of figures that say, well, in the simplest case, this is the elevation history. The trouble with that is there's for sure a lot of noise here. And, I mean, there are two issues. One is it's not just elevation and lapse rate, right? So you want to go to sites where the signal is likely to be big enough that it dominates. But the other issue, which is maybe less obvious, is that at a lot of sites, you actually have to worry about ice flow. So that site where you drilled might not have changed elevation, but the ice down here came from over there. So that adds another wrinkle of uncertainty, which we haven't yet addressed and may not address in these calculations because there's not enough information. So in short, yes, but you really want to go to sites where you have evidence of large changes. And I should add that that particular configuration through time, where it's not much higher during the last glacial maximum, it goes up and it goes down again. I should have said this. We know this is right because we have fantastic work from Perry Spector and John Stone. Perry was a student of John's, using cosmogenic isotopes to look at where the ice sheet was up on the land. And it never got more than a couple hundred meters and it wasn't higher during the last glacial maximum. And yet, most climate modelers using default topography for the last glacial maximum are using an ice sheet that's hundreds of meters higher than what our results and those independent constraints show. And yes, sorry, I think this is a huge constraint on ice sheet model physics. And I think it actually is a real problem because in the particular simulations that I showed, if you use the parameters that match our data best, then it doesn't match the modern ice sheet at all, which I don't take to mean we have a problem. I take it to mean the parameters are all wrong. So, Chris, sorry, I should have let you do that. Nice to see you, Chris.
So let's get back to the almonds and low and the sort of intrusion of warm water.
Yeah.
West Antarctic ice sheet. How much is that affected by the sort of mean extent of sea ice? In other words, suppose it was a little bit colder 200 years ago, and sea ice maybe is extending further for historic reasons. Could that change the distribution of wind stress enough to sort of inhibit this flow of cold water or warm water?
I have spent my entire life trying to avoid sea ice, both literally and figuratively. Literally because it's dangerous, figuratively because it's really complicated. And one of the outcomes of Gemma's work is you can't do that. In those simulations, and I should give Kyle a lot of credit here, he helped a lot with us figuring this out. In those simulations, what is actually happening is that the wind changes are changing the millennia along the coastline where lots of heat escapes when they're open. It's closing them through our simulations. That's changing the heat salinity fluxes, which is changing the density of the water, which is changing the circulation. Another paper that came out recently by British Antarctic Survey colleagues is actually called something like, it's not winds, it's temperature. The mechanism is the same in that changes in sea ice are affecting the salinity fluxes, but their argument is that it's actually surface temperature changes, not winds that are driving this. And yes, as you say, the presence of sea ice itself changes what the ocean feels relative to the atmosphere. So every time I think I've figured something out, it changes because it's really complex.
Going back to, I think you said at the end of your first comment that the ice core data can show that some parameters are more important than others for ice modeling, and some that you see important for this data are not thought of as much in kind of the glacier modeling community. What is an example of one of those parameters?
I'm probably speaking out of turn. Well, no, I'm not. Let me just try to explain what I had in mind here. So that plot, as I said, you can understand what's happening in the ice sheet model because we know the accumulation is low in the glacial, it goes up, and the height and how fast it then falls down again is a function of the bed slipperiness. The bed slipperiness in particular is unknown for places where the ice is currently absent. You can figure out what the current bed slipperiness is by looking at the current depth and the surface velocity and invert for that. But if the ice sheet is retreating from some larger glacial maximum, that land is, or ocean bottom is now uncovered by ice. You don't have any data. And so that's a big tuning knob that people use. My only point was that, so it's common in these ice sheet modeling exercises to tune all these parameters to match modern observations. You want the ice to look more or less like today, same velocity, same height and everything, so that you can be confident that forward projections will make sense. What we found is that the model, that particular model parameter that best matches these results is not the same one that best matches today's ice sheet. But there are many other things you can change. For example, the calving fluxes at the end of the ice, the amount of meltwater at the bed, the ice temperature itself, the flow law exponent for ice, right? There's just a lot you can tune. And so I'm not in any way claiming this is a panacea. If we do this, we'll have the answer. But it is a strong constraint on one of the most uncertain parameters. So hopefully that helps.
Okay, so ice only goes back some years, but we do have like sedimentary deposits from older glacial maximums and everything. I guess my question would be, would some of the isotopic variation of those older glacial maximums with temperature be preserved in sedimentary deposits and such?
Yeah, great question. There are wonderful ways to get at sea surface temperature in the past, to get at ocean temperatures in the past. One of the biggest challenges for the Antarctic is it doesn't have much in the way of carbonate deposits, that is forams, which are the classic way to get at the O18 of the water and the temperature of the water. There are other proxies that have been used, but the basic answer I have for you is it's pretty uncertain in the southern hemisphere. I will add one other kind of neat thing, which is that an outcome of the isotopic modeling is that you actually have an estimate of the temperature at which the water evaporated that eventually winds up on the ice sheet. And in another of Brad's chapters from his PhD work, he shows that when you do that, you get the right answer relative to the estimates of sea surface temperature from sediment cores. Not that near Antarctica, because the moisture sources are fairly far away, like subtropics to mid-latitudes. Another just quick point is that those sediment records also contain information about like when the ice sheet was larger and when it retreated because sediment fluxes increase. It's often poorly dated and lower resolution, so it can be really hard to connect, but it's something that is being done.
Well, the inverted temperature from all the different ice cores in Antarctica, you said that through borehole thermometry you could match the results that you would also invert. How far back can you use this to?
So in places where the ice is pretty deep and the snow accumulation rate is not too high, but is high enough to keep the cold snow heading down. Well, actually, you want it to be high because the cold snow's flowing downwards and beating out the warming from geothermal heat flux. And so at the West Antarctic Ice Sheet site, you see this beautiful, if it were in steady state, you would just have cold temperatures at the surface, warm temperatures at the bed. But it's shaped like this because the advection of cold. And there's a little kink because it was once colder. That's the last glacial maximum. The variations that are left are of order a Kelvin or less, millikelvin. So I forget exactly what the scale is. Of course, this is Kelvin, but very small variations. But you can then forward model various assumed temperature histories and compare. And you can do a formal inversion as well. And this is what Kurt Guffey did for this site. So in short, you can see the last glacial maximum quite well in a lot of sites. Going back further, mostly you're starting to get into, you're overwhelmed by the heat from below. Yeah. I think there was a question on the far right up there. Oh, yeah, I should say at all timescales, as long as or shorter than the ice core. Yeah, going back further in time. I don't know. But I think a key point that I was making there about timescales is that if we were only able to see this relationship, say, on glacial, interglacial timescales, there are a lot of things going on, right? The fact that we're seeing it on century timescales and millennial timescales, and everything is in phase with one another, you cannot invoke almost any other explanation. For example, changes in the ice sheet height. There should be lags and leads between the ice core sites, if that's the case. Changes, I can't even think of a way to do this. It's a fast feedback, and everything is in sync with one another. And that's where the multiple timescale point comes in.
All right, I have a question. So
Yeah.
I'm not people studying this, so I want to ask you about your second example. So when you guys model the wind shift, is that like the change really big? So that will affect the source material Australia versus Argentina, the solid materials should be very different.
Yeah, so there's a, yes, we should work together. There is we measure everything we can in ice cores, and often our ability to measure them exceeds our ability to understand them. There's dust concentrations, there's black carbon concentrations, there's sulfate and sodium, et cetera, et cetera. And a small number of people have done cool things with non-traditional isotopes, and they reflect source regions. The biggest problem that we have is that in general, you guys want a lot of ice. And we worked really hard to get this ice, and we will not give it all to you. But I know that, techniques have improved, and I do think the folks that have traditionally done this work, the ones I know, mostly are retired, and I think there's some opportunities probably to get serious about looking at this again with more modern instrumentation.
Thank you for coming out. One more thing, if you want to hear more about the PCC events, go to the PCC webpage, pcc.uw.edu. You can sign up for listservs, particularly if you're graduate students want to get more involved. I encourage you to do that. You also sign up for a calendar to learn more about PCC events that are coming our way over the next quarter. I think we'll do more of these colloquium series rotating around departments over the next year. So let me know if you want to suggest speakers or if you want to speak yourself. Let's thank Eric again.
Thank you for coming. Chris, I put this picture up for you. That's the millennia.
Thank you.
Sorry, you're kicking me out of the PCC.
So you know your step advancement curve and then where it crosses, and you said there's like a negative greenhouse effect. Is that because the surface is basically colder than the tropopause, and so that might be one way to think about it, that the radiative bounce
Yeah.
is such that if you've got a warm-up tropopause and it's so dry and cold, it has to be colder essentially, and maybe you've got like a huge inversion instead of the usual adiabatic.
Yeah.
At
No,
that point.
when I
So the
said
energy balance would just work out.
when I said I don't understand it, what I mostly mean is I see the math, but I never remember. It feels complicated to me because
Well, I was
I mean,
thinking more in terms of a simple grain model.
yeah.
Has
I
a
mean,
few different
it's all
temperatures
about
in it.
the emissivity
Yeah.
and the temperature.
Right.
And I find it easy to think about the emissivity,
Right.
but I find it confusing to think about the temperature because the temperature depends on the emissivity. I can't work out why it stays that way. But I mean, there are papers on this which elegantly show why it must be.
Oh, okay. And actually talk about something like a negative greenhouse effect.
Yeah. There's actually a paper like 10 years old that was in Nature, I think, because no one had really quite recognized this before. It's pretty cool. So, yeah, thanks. Hey, Lucy, thank you for coming. Did it make any sense? Hi.
Thank you very much for the call. I just have some question about example 1 and example 2, example 3. So what would be the implication from the result of the substantial anomalies isolated between the host and contact with the last population? Does that mean we see like climate change? No. I didn't really know either.
So if I think if you show the O18 temperature for like a typical gas, this is today and this is 150,000 years ago, it looks like that. And those temperatures are generally higher.
Okay.
It's just that one ice core site where I said that we predicted a change relative